This talk is about using a Julia language to do data visualization. Data visualization is a pretty broad topic. And so here I'm going to focus on using the Julia language or the Julia ecosystem to do data visualization. This is going to be from the standpoint of my own perspectives. Over the years, I have myself done data analysis and making plots or visualizations. For practical purposes, we do visualization for in different scenarios. For example, when you are still developing your algorithm or your computation, you may need some kind of interactive way to do your visualization. So you generate the data, you have to look at the data in a somewhat interactive way. So you kind of try and error, do back and forth to figure out your data or your analysis. For other scenarios, you may have to, once you figure out your computation or your research, then you have to make plots or visualization for publication purposes, right? So in that case, it's different from your try and error process, but then now you have to have a very polished and good looking visualization or plots of your data. In other cases, you may have to generate animations or movies for your own presentations. And also there are visualization related tasks that are beyond the typical plotting. So by plotting, I refer to some kind of XY two-dimensional plotting. So for example, sometimes the data is complex, very complex, say graph or three-dimensional volume kind of data. We have to do more advanced visualizations. These are all different scenarios that we do data visualizations. For the purpose of this talk, I'm going to focus or try to focus on the Julia ecosystem. And even in this subset of the perspectives of the visualization, there are still too many packages to cover in this short talk. So I'm going to pick and choose some of these topics. And as the title implies, this is an introduction. My intention is to introduce a few basic Julia packages for visualization purposes. For example, there is a basic plot package for Julia. And that is, as we will see later, that is not exactly a standalone package. It is actually a framework. And under that framework, there has been a number of other packages, right? So they are kind of under the umbrella Julia plot ecosystem. So that is not the only Julia plotting mechanism. I will also give brief examples of other Julia-based plotting libraries or packages. So for example, one of them, a famous one is this Makie plotting package, and there's a Vega Lite and others. So there are many. For each of them, it will take like hours and hours to cover every single attribute or options for all of these packages. So my purpose for today is by using simple examples and try to introduce the core concept. Also, I will point out the documentation. If some of them are suitable for your purposes, then you may be able to get some intuition from this talk, and then you will dig deeper on your own by looking at the actual documentations. From this list, you can kind of see that at a high level, other than plots, Julia also make it easy to connect to other existing ecosystems. For example, for people from, for example, Python background, if you're a Python user, you most likely know there's a famous matplotlib library and also several others. And sometimes people call this a pyplot. And so Julia also there's an interface to the pyplot. So from Julia language, even if you are not using the native Julia plotting system, there is an easy way to access the entire matplotlib, the Python ecosystem. And the same thing applies to accessing the R plotting mechanism, right? So you see that it's not only for Julia, but you can take the free ride on top of existing this very mature plotting ecosystems. It's also easy to access the JavaScript kind of interactivity. You will see simple examples using one of the also popular package called Plotly.js, Plotly JavaScript. library that is itself is a very powerful library. But we don't have to write JavaScript. We can still write using the wrapper or the interface to Plotly. You can write in pure Julia code, and then you can kind of enjoy or access the JavaScript interactivity. And also, we will see examples for these other packages. So that's kind of the plan for today. Basically, I'm going over a number of simple examples and try to point out some of the unique features of this Julia plotting mechanism. I created this plot from my own perspectives. As you can see here, I have been a Python or C, Fortran, MPI user for my own research purposes. And over the years, I have used Matplotlib and GNU-plot, and also a little bit of Octave or MATLAB for either computation and plotting purposes. And for visualization, I used to be a TechPlot user, and so I use TechPlot extensively. But more recently, I have slightly moving away from the Python scripting and started using Julia. And so more recently, I am kind of shifting away from kind of Python C++ combination to kind of a Julia kind of programming environment, and with and without MPI. I have also I'm also adopting the Julia plotting ecosystem. You will see that because Julia is a relatively young language, and that also implies that the plotting ecosystem is also relatively young compared to Python and R existing ecosystems. Being a young system, the downside is that it's less mature than the established Python and R ecosystems. But the plus side is that, as you may realize, and which I myself realized this, is that in different ways, the Julia interface is actually quite clean. A PairView is a kind of professional grade three-dimensional data visualization system software. I'm going to give a simple example. How do you connect Julia to PairView? So on this plot, I kind of trying to make a point that so there's an the level of interactivity for visualization purposes. And also on the horizontal axis, this is the visual quality, right? So when we are ready to present our data, say for example, to submit your paper to a journal, most likely the figures or the plots in your paper are static, right? So they have very low interactivity, so very zero interactivity. So it's a static plot on paper or on a PDF. This kind of visualization has relatively low level interactivity, but they require very high visual quality, right? Your font, your plot, your line. For example, you need to use, say, vector graphics. So vector graphics is preferred than the pixel-based images for kind of high publication qualities. So in the middle, you may have to make some kind of presentation. For example, you go to a conference, or you may have to present this to your colleagues. For those purposes, it's a mix of, you may have to kind of let your colleagues interact with your data or your visualization. For example, you set up some sliding bar for your colleagues, and then they can kind of, by tweaking a small number of parameters, they can kind of tweak and look at your visualization. So that's what I mean by mid-level interactivity, because this is for kind of a small group of people, say in a conference room, or a number of your colleagues or lab people. You still need to make your visualization good looking, but the quality requirement may be a little bit less than the kind of a final, like a paper submission. So this is kind of mid-level. On the left-hand side here it's a kind of a relatively low quality, but require very high interactivity. So this is in a situation where you, for example, you are still investigating your computation, right? Your biomedical computation, physics computation, engineering computations, and you are still figuring out your data or your algorithm, your computation. And so you need to have a very high flexibility or convenient way to look at your data. So that's why I say a debug, try and error, or you're still scratching your head trying to figure out your data. So in this stage of your data processing pipeline, you usually do not require a lot of very high quality, because probably only you or a few of your collaborators are looking at the data, but you need to have a kind of flexible way of doing this. And so for different needs, you need kind of different tools. And in the example later, you will see that there are different kind of packages, or different so-called backends of the packages in terms of the Julia packages. You will see that some of them are more suitable for the left-hand side, and some are more suitable for the right-hand side. So I just want to point it out that there is no one tool that is good for all purposes. I mean, probably will not be possible to create those kind of tools. And so each tool or each package or each kind of component of the packages, they are probably good for others. So if you try to use a tool, kind of use the wrong tool for the different scenario, that you are going to be, it's going to be very hard, and then you are not going to be happy with the end result, right? So you have to also kind of keep in mind that you have to pick the right tool for the right situation. Let's kind of jump right in. So the Julia language, it's a programming language. And if you have come to the previous Julia talks, you see that the core language itself is relatively small, although it does have a very extensive standard library. But on top of that, the functionalities come from packages. And the situation is kind of like Python and R in a sense that, so you have hundreds or thousands of packages, open source packages, and each of the package is specialized in doing certain tasks. So in Julia's case, for one of those packages called plots.jl. And so plots.jl is one of the core Julia plotting packages. And I want to point out that this is one of the important ones, but this is not the only one. So there will be other Julia packages that are developed by other group of developers, and they are equally good, or they are even sometimes you can argue that some are better than others in different scenarios. But since this is kind of the standard plotting package, so let's start with a plot.jl. And by the way, if you are new to the Julia ecosystem, you will see that the convention for the Julia package name is always .jl. So JL stands for Julia. So if you go to GitHub and other places, if you see .jl, most likely this is a Julia package. And you don't see this in other Python or R ecosystem. So it's kind of unique kind of naming convention for Julia. If you have used other tools to do plotting, say Python and R, other softwares, so you see that these plots are very similar to them, right? At a high level. So conceptually, you have to have some interface to create the command to create the plots, the scatter plot, histogram, all kind of these basic plots. There are many so-called attributes or options to control the final look, right? You want to adjust the font size, adjust the font type, and then you adjust the grid, the background color, all that. So Julia is the same. So you have all this basic command to do that. One thing that is kind of different, and I'm speaking from my own perspectives, is that the one thing special about the Julia's plotting mechanism or ecosystem is that is providing multiple so-called backends. And we will see what this means. So basically it means that you use the same command, so you don't have to change your code. And by just changing basically one line or one option setting, you can switch to a different backends, right? So for example, so you can think of, you can use the same API or interface command, and you can switch to a different kind of engines. And this is quite advantageous because I have used other programming languages, other plotting tools, and it's all good. But then at some point, if you need to change to a different, say, a backend or package, you have to change quite a bit of your code, right? So that is not convenient, because once you figure out all of the plotting command, you really don't want to kind of spend more time just because you change to a different kind of the processing engines. But if you follow this Julia's plots ecosystem, you can easily do this without changing any of it, basically by changing like one line of your code. And so by different backends are good for different purposes, right? For example, for people who are using LaTeX, you're writing your article, your reports in LaTeX. So there is a LaTeX kind of supporting backend to generate plots that can be like totally integrated into your LaTeX processing system. You can also generate JavaScript enabled plots, so that the user of your plots, the user maybe yourself or your colleagues, they can open your plot in a browser, and then there's a certain level of interactivity there. And also you can generate either the images or graphics and other purposes by switching to the right backends. And after those basic tools, I'm going to also talk a little bit about something called recipes. So if your work or your workflow, suppose your day-to-day work, you have to make the same kind of plot again and again. You don't want to copy and paste the big chunk of code just to generate the same type of plots. What people do is they copy, say, 20 lines of code and change like 1 or 2 lines in order to generate the new plots. And so if you realize you are doing that kind of thing every day, then recipe could be a good way to develop your own plotting recipe. So recipe sits on top of a plot system. So basically, this is a set of your own script or your own library to make the kind of plot that you do. And so if you do this, then your typical plot will take only like 1 line instead of 20 line copy and paste every time. So we will see 1 or 2 examples of this. And also there are something called the themes. So for a plot, other than picking the kind of symbol size, line width, and axis, there are certain popular themes that people prefer, and we will see. And also I will give some examples of how to make the animation in a Julia style. Okay, so that's kind of the plan for today. And so before I start, I want to kind of make a few comments about the Julia example code that I use. Since I'm going to jump around across different packages, and if you came to the talk about Julia package last time, there we talk about kind of how to install Julia packages. And so Julia, the core language itself, comes with a package manager, which is quite powerful. And if you have used other package managers, you realize this is one of the good ones. The Julia approach to manage package is that for each project or each your project is like a folder that containing your code for certain purposes. And you can think of a project like if you use GitHub or Git, this is the one repository. If you just use your typical editing, this is like the folder of your Julia code. So that's like a project. So in Julia's case, there's a TOML file called project. So this file contains the information about the packages that will be used for this project. Just like Python and R, so Julia has like thousands of packages, and you don't want to load all 1,000 packages into one single place, because there will be conflicting packages. So you don't want to mix. Some packages are okay to put together. Some packages are kind of, they don't work well together. In our case, I'm going to create folders for each package, which I can show you so you know what I'm talking about. I suppose you can see my screen. So this is the GitHub repository that I'm going to send you, and I'm going to make some final changes after the talk, but I will send you the link. So here, you will see I have like a number of directories, and each directory, for example, if I go to this one, each folder has its own project, TAML file, and the TAML file contains only the packages that will be used for this folder. And so this is a good approach to manage packages to avoid collisions. So you have a kind of a minimum set of packages for this project. And so if you go to other folders, for example, another folder, and you will see that the project file, this is a separate TAML file, and it has its own, there are only 3 packages here. So there were more in my other folder, and this is only 3. So this is the way to handle package and to avoid collisions. But to do this, if you are going to try this, you are going to start your Julia with this -- project equal dot. Dot means the current directories. You're going to start your Julia like this in order to use the correct project.toml file. If you don't do this, if you just run the Julia, Julia will just use the default TOML file, which may not be the right one for running the particular packages in that folder. Right? So if you are within certain folder, right, this is one of some arbitrary directory on your computer, and you start Julia with project equal dot. Dot means this current directory. You are going to see this, and when you activate your Julia package manager, you're going to see this current directory. Right? If you do this without a project, you are going to see only the general, the top level Julia default environment, which may not be good for this particular folder. So this is something I want to point out, because this can be a point of confusion if you are new to Julia package management. And of course, you also have to instantiate if you haven't installed these packages, in addition to activate the folder, you also have to instantiate the folder in order for Julia to download all of the packages into this environment so that you can run the code. But if you do all of this, then the code should be pretty robust, and you should be able to run this on different platforms. And also, just another note, this is generally about Julia package management, not necessarily for visualization, but I think these are important if you want to try those examples yourself. When you install Julia packages, and typically, for example, if you are going to install the plots package, inside the Julia package manager, you just say add plots. And so this is most likely 90%, and more than 90% of time we do this. But this will automatically install the latest version, right? And this implies that if you do this, say, a month ago, and if you do this today, you may be installing different version of plots, right? So the version you install today may be slightly newer than the one that you installed last month. And normally that's okay, but in certain situations, that minor change of versions, and for most packages do not do this, but there's a remote possibility that latest version may be conflicting with some other packages. So basically, you don't have a deterministic environment, right? Because always pull the latest, and latest is a function of time. So most of the time it's okay, but then you know that it's not exactly deterministic. Another way to do this is to install a particular version. Right? If you really care about, if you want to really make your environment deterministic, then you have to kind of stick to a particular version. If you do this, then every single time it's going to install exactly this version and this version only. And so that is one way to guarantee that your environment is deterministic, right? But so I want to say that most of the time doing the latest version is fine, and it's probably good, because then it also kind of automatically run with the latest version, right? Because if you stick to one version and keep doing this for a year later, there's a very new latest version that fixes a lot of problems, but you are still sticking to the old versions, right? So there are kind of pros and cons in these approaches. And also the package manager also allow you to install a particular branch of the Git repository. And so this is another syntax. So hash means that this is a branch name. If you are an advanced user, you want to kind of point to one of the GitHub branch that this is a way to go. Right? So there are different ways to do this. And then, but if you want to know more, you should go to see the Julia package management documentation. So here is a kind of a quick thing, and I don't want to spend too much time here, but I think this is kind of important to know. So if you empty directory here, I start Julia with --project dot equal dot, right? Dot means this folder, and I install one particular package, right? And because I haven't done this before, it's going to take a long time. So let me kind of fast forward. So so you see that it's downloading, it's pre-processing, it's compiling. And then so you will say 27 successfully compiled, right? And just a reminder, although Julia program looks like a script, it is a compiled language. Right? It's compiled by basically like a C compiler. So when you install a package, sometimes it takes time, and people complain that Julia is slow, but it's not. Julia is not slow. Julia is because the compiling takes time. And once you do the compiling, then Julia code is going to be fast. And so in this case, it pulled down all of the dependencies. It compiled 27, and there are like 100 something that are already compiled on my system, right? So it only compile what's needed to be compiled, and the whole thing takes like more than a minute, right? So if you are impatient, this may sound like a long time. But after that, then the package is installed. And I didn't specify the version, so it's installed this latest version, or something close to the latest version. And notice that, and also it updated my project TAML file. This is not my default environment TAML file. This is TAML file specific to this particular folder that I'm working on. Right? This is my my current environment. And if you do the same, for example, I have installed those packages before, and if you do this, from a different folder, right? And I do the same thing, and I install the same package. And this time, if you watch in real time, you realize that this is done in like 2 seconds. And why is it so fast? Because Julia detected that everything has been installed, right? So it's basically just update your project file and it comes out. So if you have already installed those packages and you are starting a new project folder, installing packages takes like less than 2 seconds, right? So just want to point this out because I think last time some people asked, and this is a kind of a small point of confusion. And so I want to kind of point out. So let's come back to our main topic, Julia visualization. Just like any other plotting system, there are multiple components for plot. And so in Julia's, in particular, the Julia plotting mechanism, or the whole figure is called plot, right? So in different software system for plotting, some package call this a figure, and some packages call this is a plot, right? Some other Julia packages I'm going to introduce later in this talk call this whole thing a figure. But in terms of a plot.jl, plots.jl, the whole thing is called a plot. And a plot can contain multiple subplots, right? So, and you can actually create very complex layout to do the subplots. And in this case, I have 2 subplots, right? This is like a tree. This is a tree has 2 branches, and each has one subplot. Each subplot has a number of components. So you have the axis, you have the data itself, it's called series, you have a legend, you have title, you have the labels, right? The ticks here, axis ticks, and the axis labels. And also you have the maxima or range of the axis, right? So all of this. And also you see on the left and right, you see the fonts are different. One is the typical, like a Microsoft Word or kind of typical Word font. On the right, you see this kind of a font that looks like your mathematical textbooks, right? So this is a LaTeX font. for mathematical equations. And also on the plot, you may have grid. It's very light. You cannot see, but it's grid. And also you can control the colors or transparencies of either the plot or other components. And the plot itself will be output into different formats, right? Could be HTML for the web display, could be some vector graphics, SVG or PDFs, or it can be a pixel-based PNG or JPEG or other image formats, right? So this is kind of the different components of a plot. For practical purposes, the way to generate this is learn to how to control each component. So each of these components is associated with a number of so-called attributes or options in Julia's plotting API. The next few slides, I'm going to show a number of kind of simple plots, and it's probably too simple for the audience here, but I just want to kind of set the foundation. And you can basically create those simple plots using many other softwares, right? Like GNU-plot, MATLAB, or R, Python, and here we do the Julia. And the purpose of doing the simple plots is I want to kind of illustrate some of the kind of Julia style of programming to make plots. For example, and also, of course, these are written in Julia. So if you are new to Julia, some of the syntax, Julia syntax may not be very obvious. But I think most of the time, you can kind of, by looking at the code, you can kind of figure out what it's doing. So in this case, I have X, Y data sets, right? X is like the axis. In this Y case, this actually contains 3 vectors. So Y has 3 components. The first component is a sequence of number. The first sequence of number of Y is a sine of X. The second sequence is cosine. And the third sequence is some sine multiplied by exponential, right? So although it's Y is like one variable, it has actually 3 sequences. And this is one typical way to do plotting in Julia, right? If your data is already in a table form, a table means you have like multiple columns, and usually the interface, the plotting interface, automatically recognizes those columns. And if you don't say anything, it will just plot all of the columns. Right? In this case, I just say plot XY. This is I just want to control the thickness of the line. Otherwise, it will just plot all of the columns in Y against the X coordinates. Right? So there are always 2 vectors here. The first one is the X coordinates, and the second one could be a single sequence, could be multiple sequences. In case of multiple sequences, like in here, it will just plot all three for you. And the colors are picked by the default called palettes, and I will kind of also explain a little bit later. After that, the plot will not have any decorations, just the lines. You can modify the plot by using also the plot command. And you see, if you are new to Julia, this may look kind of strange, but this is Julia's convention for the function names. If you see a function name with an exclamation at the end, it means that this function is going to modify its object. So in our case, our current plotting object is P1, right? So when I create a plot, I also assign this to the object. In a current object, when I call plot exclamation, I'm modifying the current plotting object. And because in this case, I'm adding the titles, the labels, and the limits to my existing plots. So I have to do the exclamation. If you don't do the exclamations, it's going to create a new plot, right? So that's, in a way, it's good in a sense that in the syntax clearly show that the function is modifying your object, right? So the code kind of document itself. And in other languages, you may have to kind of know the code, or you have to guess what the code is doing. But Julia kind of uses syntax to kind of explicitly say that I'm modifying the object. And the object is by plotting the plot object. At the end, I can save the plot to a file. You can also save to other formats. In this case, it's a PNG form, which is the end result is this. So this is kind of the flavor of the basic plots. And you can do more complex thing than this. Just want to point out that in Julia, you can also directly pass the functions to the plot command. In the previous case, right, the plot x, y, this x and y are data elements, right? Each x and y are one or multiple sequences of numbers. But also, you can also pass functions or arrays of functions into the plot command. And the Julia plot automatically recognizes and will determine certain things for you. For example, in this case, if you look at all the options, so I'm plotting x against, so x with the arrow sign to a function. This is a Julia's way to define a function in place, like anonymous function. In this case, it's a array or a list of anonymous functions. And this is a starting point, end point, line width, and then the limit of the x axis and y axis. If you think about it, you see that you did not specify how many points you are going to plot. And so this is one of the kind of the built-in feature in Julia, is that sometimes we want to just make a plot of a function, but then the plot function can kind of automatically figure it out, and then make the function look very smooth and determine the number of points for you. So you don't have to worry about that. I want to kind of point it out. This is one convenient small feature, but useful. You can also make plots in this fashion. So you can create individual plots. For example, I plot one set of lines here. So in this case, I'm plotting a function, a sine function with a shift. So in this case, A is a shift in the sine signal, and that shift A is going in a range 0 to pi over 2. And I'm going to take 3 points in this interval. And for each value of A, I'm plotting a sine x minus A, right? So your sine wave is shifted by a certain amount. And so this is my P1, right? So this is my first plot and the second plot. After making these two plots, maybe at some point you decide, okay, I want to make one single plot that contain these two previously generated plots. And the way to do this in Julia is simply you just make another plot command here and just plot this P1 and P2 here. And then you can specify the layout. And so you don't have to go back and change this plot to subplot or other command. You can just compose your new plots by using existing plotting objects. Right? So I find this quite convenient. Small thing, but quite convenient. And you can specify the layout. So in this case, the layout is 2-1. 2-1 means 2 rows and 1 column, right? So like in this layout. And in this, another thing I want to show in this case is that it's when you plot multiple lines without specifying the colors, Julia will pick up the colors from the palette. And the default palette is a certain number of numbers. And if you have more lines than the number of columns, the number of the colors, Julia will cycle those colors, right? So if you have too many lines, you are going to see that the colors are going to repeat themselves. But other than that, it will pick up the colors for the default palette. But you can specify a different palette, right? So for example, the first one, I'm using the default palette. The second one is I'm picking one of the kind of built-in palettes, and the documentation page has many palettes you can pick to pick the color scheme that you like. So this is something I want to kind of point out. So you see that the color schemes are different, right? So this is one set of palettes, and this is a default set of palettes. Another thing that if you are new to Julia, you may see that the syntax is also kind of weird, right? A column followed by a name. And in Julia, this is called a symbol. Right? And I'm not going to explain the details here, but this is one of the kind of Julia specific syntax. You can think of a symbol like more or less like a pointer to some object. It's not this is not a typo. This is part of the Julia syntax. And also you can create different kind of plots. In this case, this is a heat map. And the thing I want to show here is that, so palettes are kind of for discrete, more or less like discrete colors for lines, right, or symbols. And there's something called the color gradient. So for example, you want to make this kind of contour plots, there is another set of color gradient, color selections for different purposes. And the documentation has a long list of color maps you can pick from. In this one, we picked one of those, one of the common color scheme called jets, right? So it's a typical, like a very bright, red to very bright blue kind of jet color schemes. You can organize your plots, subplots, if you have several of them. If you just make a number of plots, let's say in this case, I have 4 columns. I have a 20 by 4, say, matrix, right? So I've basically, you can visualize this by, this is a table, and I have 4 columns. Each column is a random numbers. And so when you say plot this 4-column table, Julia is going to generate basically 4 lines in one plot. But if you say layout equals to 4, it will kind of smartly kind of split your plots, and you have one column per plot, per subplot. So here I didn't specify the actually exact layout, but if you just say if I have 4 plots, then Julia will kind of set out the layout for you. But you can override this by saying I want a 2 by 2 layout, which is the same as the default. And you can also, I want a 4 by 1. Right? 4 by 1 means 4 rows and then one column. Right? So you are going to have this kind of a 4 plots kind of stack on top of each other. And you can also specify the size of this plot. So this is coming from my previous size. So I think this is like a 1024 by 768 pixel size. You can specify, I have a very wide width and I have a small height, right? So your plot is going to be like this. So you can specify all of this property in one command. And you can do this in other systems, but this is Julia's way of doing it. And again, you see this kind of column red. So this is the color is red. And this is just column red is a kind of like, you can think of this like a pointer to the red color in Julia syntax. And also, you can also specify different frame styles. In this case, the first one, frame style means the bounding box of your plot. In the first plot is a none, so there's no bounding box. The second one is a box, so you have solid line on all edges. And the third one and the fourth one is just different styles, right? So more and more we see this, so you control the look of your plot by using these attributes. You can also very flexibly specify the heights, right? So I want this tool to be shorter and this is high. So you basically just specify the percentage of this plots. At this point, nothing too exciting, just the typical plots or subplots that we typically make. If you want to kind of put more plots in one figure, in Julia plotting system, it's actually quite easy to do. And actually, I find that the syntax of this is consistent with how you compose matrices in the Julia language. In Julia, you can create small kind of a sub matrices, and you can superpose small matrices into a big matrix. For example, you are solving a system of equations. This syntax is kind of similar to that. So there is a macro. So in Julia syntax, if you see an @ sign, so something was followed by a name, this is a macro. But a macro is not exactly a function, but it's a kind of usually is a convenient way to create some object. And so in this case, there's a layout macro. And this layout macro, I'm going to create the following layout. you don't have to worry about some details in the syntax, but I just want to point out the way, the kind of the logic behind this. So suppose this is the final plot I want to create. So I want to have a tall plot on the left, and I want to have a kind of a short plot at the bottom. So if you look at the structure, you see there's one column here on the left, and the second column on the right. Within the second column, I have a 3x3 on the top and the one plot at the bottom. To create this layout, at the top level, I'm going to create one on the left and a one big one on the right. And the one on the left, I want to say that this is 30% of my space. So 30% width, and this is 70%. So I'm creating a 30%, so 0.3 W, W means the width, and with a block of other things on the right. So this will create this, the first column, first plot, and then the rest of it. Within the second block, I have a 3x3 on top, and I have a 0.2, so 20% height at the bottom. So the 30% on the left and the 20% at the bottom kind of already imply the remaining size for the 3x3, right? And the remaining size, I said this is 3x3, so I didn't specify the partition in height. So Julia is going to equally divide the space into 3x3. Once I have this layout, I can make the same plot command, but I'm adding this attribute called layout, and this L is this object that I created previously. And so it will make the subsequent, it will basically insert all this data, or the lines and symbols, the plots, into the right plotting components. So in this case, I have a total of 11 subplots, right? One on here and 3x3, so 9, and then one on the bottom. And of course, the content of the data is kind of nonsense. It is just to show the syntax. So this is a 11 column table, right? Each column has 10 numbers, and just for convenience, I'll generate the random numbers. If you have a meaningful plot, this will be the data that you load either from a data file or from your other Julia functions, or from a file, right? So, but here we just create some number just to show this plot. If you set up the right attributes of the command, or use the right macro, the code tend to be quite short, and then you can kind of focus on the visualization itself, not the coding the details. And like I mentioned earlier, so if you find yourself making the same kind of plots again and again, or if you are making, and I think most of us do, I mean, when you do a certain type of analysis, you always create kind of similar kind of plots, and maybe in your field. You may want to, and once you become familiar with the Julia plotting mechanism, you can consider something called the recipe. And the recipe is a mechanism that is built in as part of the Julia plotting infrastructure. Simply speaking, a recipe is some kind of, you can think of a recipe like a function that you write for yourself to make certain kind of plots, right? For example, you always want to have a green color background, for example. And instead of adding this color green to every single plot that you make, then you can create your new plot command or new plot function that always use the green color as the background. So something like that. And you can do much more complex thing than just setting a background color. And of course, you can think, oh, I can write my own Julia function just to create my custom plot, right? So that is right. But then the recipe provides you with more advanced features, right? So I just want to point it out this. Not everyone needs this. And also, even if you don't write recipe yourself, maybe if you are going to use the Julia plotting kind of infrastructure, maybe your research field, I mean, some people will create your field topic specific recipes that you can use, or you can copy and modify it. Just like any other Julia kind of software engineering structure, the recipe mechanism in Julia plotting is written as a package itself. Right? It's called the recipe base, and you can use this recipe base to create your own recipe. And for example, suppose that I'm doing a statistical analysis like all the time, and so in my workflow, very often I want to compare the correlation of two, say, vectors or two series or whatever you call them, or two sequence of numbers. The plot I always want to create is I want to have a histogram of my sequence of number A. I also want to plot the histogram of the other sequence, and I want to compute their correlations. I want to show the correlation in colors, and I pick one particular color scheme. So suppose I find myself always making these kind of plots, because for my day-to-day analysis, I always want to look at visualize the correlations with the histograms. If you coming from a previous example from previous slides, I know how to do this, right? This is actually a 2x2 plots. So this is the first column, and the second column, this is empty. And this is the second row, and this is the second column of the second row, right? And you just rotate your XY into this 90-degree. You can make a histogram, and then you can compute the correlation, and you can show the correlation in using a particular color map, right? So you can do all of this using the knowledge that we already know. Someone create this called marginal histogram, and this is created as a recipe, Julia plotting recipe. And actually, this is one of the recipe in a package called StatsPlots in Julia. If you're interested, you can go there. And the StatsPlots is one of the package under the Julia plots organizations. In there, if you look at the code itself, you'll see that it's actually creating a layout that we just talked about, right? And you're creating this is a 2x2 layout. This is the upper left corner, upper right corner, which is empty, and this is the upper left lower corner, which is a correlation, a 2D histogram, and this is 90% of the width, right? 90%, and this is 10%. And of course, if you don't like this percentage, you can just change this, and then you have your own custom-made recipe. And so this is the one piece of the code in this recipe, right? So by writing this recipe, now if you have XY sequence or numbers, then you just call the recipe, right? Just like a function. And then you can specify certain arguments. And so by one command, you get your kind of plots, right? And like I said, you can always write your own function to do this, but using the recipe mechanism, there is a small learning curve. You have to learn how to use this new package, but then you can have access to more functionalities. So for long term, this is a good way to build your own library, plotting library for your your domain specific plotting purposes. So this is what the recipe does. And the next, so we have seen a few kind of plotting examples. There seems to be like infinite number of attributes you can control. And so I want to show you in the next few slides, I just want to point this out. And we are not going through all of the attributes, but I want to show you how to kind of query or look up the attributes for plots. And so at the top level, we want to understand that the Julia plotting divide those attributes into 4 groups. One is something associated with a plot. So remember the figure I showed earlier, plot is kind of the whole thing, is the whole figure, right? So this is the attributes that will control the whole figure. And then there are attributes that control each individual subplot. And also there are attributes that control the axis, right? So axis is, each subplot has multiple axes. And then within the axis, you are going to put your data points or lines or symbols or markers. And then so there are also attributes that control, say, the color of your data and so on, right? So the main command to access all of these attributes is called plot attributes, so plot attr. And in Julia command prompt, if you run plot attr, it will show you, it does have 4 broad categories. And to kind of look at the available attributes within each category, you have to put the category name into this function called plot attributes. But you notice that you have to put the column, because this function accepts the attribute name as a symbol. Symbol is a Julia specific terminology. So basically just put the column and then the name. In this case, the series attribute, the group series has the following so many attributes, right? But you can kind of see this is the arrow bar, Y arrow bar, and you can see the labels, right, that we have used earlier. And there are contours, so there are different line colors, right? So you have different things that you can kind of play with or look up with. For the access, you also have a huge number of attributes, and I'm not going through this one by one. Just want to show you. So the column access, you see all of this, and the subplots also have a bunch of attributes. Also, plots also have a number of attributes. But how do you find out the property of each attribute? For example, if you enter the attribute's name, so this attribute, if you enter that name, say foreground color, for example, in this case, you enter that attribute name with a double quote. You see the difference in the syntax. If you do a plot attribute and one of the 4 name as a symbol, it will show you a list of attributes. If you put the attribute's name, one of the attributes name with a double quote, so double quote in Julia is a string, then it will show you the property of these attributes. So it will show you the data type of the attributes, and also it will show you the aliases of the attributes. So this is another thing in Julia, is that each attribute has a number of aliases. So as we will see in this example, so for example, the frame style that I used earlier to determine the style of the bounding box of your subplots. So when you say plot attribute frame styles, you say this is a symbol, right? And also this frame style has the following aliases. Aliases means that they are equivalent to the official name frame styles. So in the place where you have to specify a frame style, you can simply specify box, right? They mean exactly the same thing. And so some people find maybe some of the aliases are easier to remember than the official names, right? So this is kind of the way you can, so, and otherwise they are equivalent, right? Other than the differences in the names, they are the functionality wise, they are equivalent. And also it tells you that the available values for these attributes are one of these. So this means that you are going to, in your plot command, you are going to specify a frame style equal and one of these symbols, right? So that's why in the previous example, I said frame style equal to, say, column a box in one of the subplot. And the other one, I said frame style equals to like a column grid. So this is the way to specify those attributes. So all of these are available in the Julia command line. Strictly speaking, you don't need a website. If you do, you can go to this web, open your browser to one of these pages, then you will see the exactly same information, but you can also kind of poke around by using the command line in the Julia repo. Right? So all of the help informations are there. We know the basic plotting commands, and we know the recipe, right? So recipe is a way to write your own wrapper, custom code. And I want to point out there is something called the themes. If you are coming from, for example, the R, if you have the R users, and one of the kind of famous R plotting packages called this ggplot2, right? And ggplot2 has its own kind of style and syntax. And also several other kind of different themes. So theme basically is some kind of color scheme plus background color plus the style of the plot. And so if you want to kind of use, and there are several existing theme you can use directly. So for example, if you make the same plot, but you just want to adopt the ggplot theme, right? You want to make the plot that look kind of the same as your friends' R plots. So you can just simply say theme is ggplot. And again, this is a symbol, so column ggplot2, and then you make your plot, and then so your plot command remain the same as the basic command, but then by adjusting the theme or picking the theme, then you can generate very quickly generate the look and feel that you want to use. So for different purposes, different themes are good. Any of these Julia packages are open source packages, and the codes are written in Julia. And Julia, like I said, Julia is a compiled language, but it looks like just like Python and R. The code is actually quite easy to look if you become familiar with the syntax. So you can always add your own themes, right? Once you become more familiar with the Julia language, you can take one existing one and then tweak and then modify and create your own theme. And then you can just use theme column like my own theme, like you create your own name, and then you have your own kind of custom style of plot. So themes and recipes are kind of additional mechanisms to help you to customize your plots in a kind of systematic way. So you can just copy and paste kind of same block of code again and again all over the place. So the next the topic I want to cover is how to make animations, simple animations. Here again, without going into too much, like every single attributes of making animations, I want to point out several important points. So in this case, I'm making parametric function plots. As you can see, I'm making the first plot is a line plot. The second plot is a scatter plot. Scatter is like only plot in the symbols. And then I'm making a plot P1 and P2, right? So by default, it's a 1x2 layout. And then I create animation, and the animation is created by using this animation function. So this is creating a kind of empty animation. And in the animation, basically, if you think about animation, is like a sequence of images. And of course, you can write a code to create individual images, and I do a post-processing to compose those individual images in individual shots into a movie or animation file. But a cleaner way to do this is create an animation object, and then within the animation, it's usually some kind of loop, right? Because to create animation, you need to create a sequence of images or sequence of plots. And then you are going to set the frame per second to determine the kind of the speed of your movie. Within the loop, I'm going to vary the value of x from 1 to 2 pi, right? And in the 1 to 2 pi, in this range, I'm going to generate 20 points, right? So that's the range this range function means. For every single value of this x, right? So first x is 1, the second x is 1 point something, and the 20th x value will be 2 pi. So for each value of this, I'm going to make a plot. And how am I going to make a plot? I'm going to make a plot. I'm going to push new points. So this is an x value followed by 4 different functions, and 4 different functions corresponding to 4 different curves. So I'm going to push one set of data points into my plotting object, which is P. And like I mentioned earlier, push exclamation means that this function will modify your object. But the plot doesn't have the exclamation, meaning that I'm generating a new plot, and which is so basically you are pushing data points to your object, and then you're making a plot. And I'm going to collect this current plotting the plot or the figures or the image into the animation object. At the end of this object will contain all 20 shots of my animation. But this is still in memory. And so I need to kind of dump this 20 frames into an animation file. There are different formats that are supported. Two of the common ones. One is the animated GIF. This is an animated image file. And the other one is the MP4, which is quite portable. You can pretty much play this on any device these days. And you don't have to output both, but in my case, I just convert this animation object into the format. So you see that there's a pattern here. There's always create the object, and there's a separate process to convert your object in memory into a particular file format, right? And in this process, I can specify the frame per second. By changing this number, the movie speed will be different. The GIF is convenient in the sense that it will start displaying the animation whenever you open it. But the video is good that you can move back and forth, right? So depending on the purpose, you may pick one of the two different formats. But there's a downside in this plot. If you compare left and right, you see that the right one, right? Even before you start plotting, you see the range doesn't change. And the plot on the right, you see the range of the axis is changing as the new data point appears. And so this is a kind of a side effect that can be easily fixed by tweaking the initial plot, right? So if you think about it, if your initial plot already spanned the maximum range that the data is going to use at the end of the animation, like the one on the left, there is no change in the axis, right? So depending on the purpose, maybe you prefer the one on the right or on the left, right? Sometimes the moving axis may be annoying, but other times some people prefer this because it kind of adds a kind of a flavor of something is changing for the audience. I want to kind of show a simple animation that create simple plots using a kind of real data sets, right? So far, we are just using the dummy random numbers or some sine, cosine functions. That is not too exciting. So suppose you see, and this is the COVID-19 season, so we are going to look at some COVID-19 data sets. So if you go to the CDC site, right? So one of the CDC data tracker site is the COVID-19 vaccinations, right? So in the US, there's a daily number of vaccinations, COVID-19 vaccinations, and there's a bar plot. This is the plot in the CDC website. Underneath the site, there's a download link, right? So you can actually go there and download the data. The data is there available. And suppose you want to create your own plot like this and look like this, but you want to create an animation, right, for some purposes. And so you can download the data and create your own animation. And now we know how to do this in Julia, so we can kind of completely do this in Julia. And there are, of course, multiple ways of doing this, but I want to show you one way to do it and kind of a natural way to do it, alignment with the Julia kind of syntax, kind of following the Julia convention. One way to load this kind of CSV file in Julia is to load it in. So this is a CSV file. This is a Julia package called CSV. And this is the data file that's coming from the CDC website. And the data file has some header and missing values. So these are handled by the CSV package. Once I have this file, it's convenient to convert this into a data frame. So if you are from Python and R, you may have heard of the data frame concept, and Julia has a similar kind of setup. So a data frame is basically a table, right? Like we have seen earlier. If you format your data into the tabular form, so table means you have multiple columns of data, then it's quite easy to make plot because the the plot mechanism kind of understand the tabular format quite well. After you get this data, and actually there are many, many columns if you actually try this. So we are going to kind of strip down the data by cutting out some columns, and we're going to focus on one of the columns called admin. So this means the number of doses, vaccine doses administered by the US government. So we're going to pick some columns, and I rename some column into certain meaningful names. And because the data is divided into different groups, we kind of combine the data in a certain way. Some numbers are split across multiple rows. We basically are kind of merging them into one single row for one particular date, because we want our plot to be based on so every date should have only one total number of doses. But the data file has maybe multiple lines for one date. So we have to kind of combine those methods into one. So at the end, this is the clean table DF2, data frame 2. And we are going to make a plot. Just like a CDC side, we're going to make a bar plot. Each bar is going to show the number of doses per day. And we kind of follow the same terminology. We create the initial plot, and we create the animation object. We go from day 1 to this is number of rows in the data frame 2. So basically from day 1 to the last day available in the data file. In each value of X, so basically each day, I'm creating my bar plot like this. So I'm adding my bars as I go. So that's why initially there's only one bar, and then as you go, you have more. You have more number of days, and then you have more bars, right? And then we generate the bar. But then you see that the axis is moving, the y-axis is moving, right? So this may be too annoying. So we can kind of adjust this, and this is the kind of the details, but then I think it's a useful fix, is that you can, when you create the initial plot before the animation, you can figure out the maximum range of your data. Right? You already have the data, and then so you can figure out the minimum and maximum range. And then when you make your animation, then the axis will be kind of static, and you only see the bar going from left to right, right? And of course, you can output the final output into either GIF or MP4, right? So this is kind of a typical way to create simple animations. And of course, you can combine different features and to create very creative, very kind of fancy, advanced animations. But hopefully, this shows the basic idea of creating the animations. And so far, we are looking at kind of the kind of basic features in the Julia plots.jl package, and also some of the extended components. There is another plot package called Plotly, and Plotly has become quite popular if you are looking into some kind of interactive web display of your plots, right? So if you are interested, you should go check it out, right? It's a very interesting and powerful graphic libraries. And this is built on top of D3. So D3 is another JavaScript-based library that for kind of web animations and interactive graphics. And so Plotly is very powerful, but then most of us, I'm assuming that you are not one of the JavaScript experts, right? We may know Python and R and maybe Julia, but then we don't know much about JavaScript. And so fortunately, in Julia's case, you can easily access the Plotly functionality directly from Julia. What is better is that you can actually use the same plot interface that we have seen earlier, those plots.jl interface. And by switching the backend to Plotly.js backend, you don't have to change your code, but then suddenly your output is a JavaScript-enabled HTML output. So for example, I have a Julia library here. Before you make your plots, you run this command called plotly.js. This is one particular command to enable the Plotly backend. Of course, you have to install this plotly.js Julia package first. If you go to our GitHub repository and you will see those set up in the project.toml file. But otherwise, in your code, the rest of the code is exactly the same as what we have done earlier, right? Just a simple standard plot command in Julia API. But by adding this one single line, of course, I also specify the size of my canvas. When you output your data, or when you output your plot, you can output as a SVG, like a standard vector graphics. If you output your data, your plot into HTML, it's going to be JavaScript enabled. And let me show you what it looks like. So this is the out. So I run this code. We run this code, and this will be just like any Julia code. And then we set the output to be HTML, and you open this in the browser. So you notice that when you move your mouse, you can see when I move my mouse onto my data point, you see that the data is actually showing the numbers, right? So this x-axis is 4, and the y coordinate is 170. So you can kind of inspect your data conveniently, and also you can also zoom in your data, right? So and you can and by hovering your mouse over to the data points. So in this case, I'm still writing the exactly same Julia plot command, but just by enabling this plotly.js, I can easily get the HTML output with JavaScript enabled. So for some application or for some people, this is actually quite convenient, right? So and once you get this HTML, you can say put on your website, or you send this file to another person, and the person can open this in a browser. And I think 99% of the devices these days has a web browser or more than a browser. So this is kind of a convenient way to enable JavaScript without knowing JavaScript, right? And you can take a screenshot, and you can save your image. If you want to save into as an image, then you can do so by saving it. And so this is another way to export your plot into interactive JavaScript. This is another example, right? So this is a probability density plot of certain distribution. And this is the area under the curve. The summation is going to be 1. So this is the probability 1, if all random numbers combined. And so again, you can kind of zoom in your data, and you can kind of move across. You can use your mouse to inspect your data points, right, and see the values. And so if you need this kind of functionality, plotly.js could be a good option, right? You basically don't do anything. You just install the package, add this one line, and then you are there. Of course, to access the more advanced JavaScript, you may need more advanced kind of setup. But I find this is an easy way to have a basic JavaScript interactivity is very, very easily without changing much of the code. Like I mentioned earlier, there are other very powerful Julia plotting packages. One is Makie, which I will give you like one or two very simple examples. And the other two I want to mention, we are not going to cover today, is this thing called Vega Lite. And the other one is Getfly. So without showing examples, I want to show you the website. So this plot, this is a Getfly. By looking at the kind of a plot it can generate, so you can kind of see the look and feel of this plot. And just like a Plotly, you see when you move your mouse over, there's a certain interactivity built in, right, for this in this package. And so this, for some people, this is the kind of a plot they prefer. And you see the look and feel, the default look and feel are different from, say, a pie plot or the Julia's default plot kind of the style. And so this is one of the powerful package. The Vega Lite is another kind of also powerful plotting package. And just by looking at the screenshot of the examples, you can get the sense that this is like a publication quality kind of images, right? You can have maps, or you can have this kind of fancy looking plots by using this the syntax of Vega Lite. So it's more powerful. Of course, it's also more advanced. This has a different design principle in mind. So the logic and then the structure is different from the Julia plots.jl that we have just talked about in the last hour. If you need this kind of functionality, there is a Julia interface to this. So there's a Julia Vega Lite.jl package that allow you to write Julia code and then to access the functionality available in Vega Lite. Vega Lite is not Julia. Vega Lite is another library, and the Julia's Vega Lite interface is the interface to access the functionality in Vega Lite or Vega library. So that's the other two kind of powerful package I want to mention, but we are not going to cover today. In this case, the getFly, this is another kind of plot that can be easily generated by getFly library from Julia interface. Makie is interesting in a sense that it is a powerful system to generate vector graphics. This is separate from Julia plots, but it's also another way to make beautiful plots. And I want to give you a few examples in the next few slides just to get a taste of it. There seems to be a confusion that when people look at the Julia plots and they think Julia plots is one single package for plotting, but that's not the case, because the plots, Julia plots.jl is more like a framework. And under the plots.jl, there are several satellite or dependency packages to specialize certain things. And Makie is another plotting package. For this Makie framework, there are three different backends, just like plot.jl has different backends. Makie also has three backends, and each backend is good at certain things. The Cairo backend, Cairo Makie, is good for generating vector graphics, right? So this is a publication quality vector graphics, a PDF, SVG kind of images, not images, vector graphics. There's also a GL Makie. So this is for OpenGL support, right? So of course, this will require some GPU support, but these days, a normal computer has a decent GPU. So normally this is not an issue. And OpenGL means that the focus here is on the screen display. With the GPU, you can do certain fancy things on the screen. Like if you play like a high-end video games, you see that you can utilize GPU to do certain projections and rotations and some other features. There is also a third component called the WebGL, right? So the WGL Makie. And this one is relatively immature compared to the first two, but this is also rapidly evolving, right? So maybe in the next few months or a year, this will become more mature, and then it will have support for WebGL. So you see that Makie is also one quite competitive ecosystem to do plotting in Julia. So I want to mention, just like the plots, this Makie thing is organized into like two layers. On the top, there's something called abstract plotting. So just like plots.jl, this defines the interface to call the plot commands. Underneath this abstract plotting, there are specific backend implementations. Right? So basically, this will enable you to have basically same plotting command, but then by switching to a different backend, you can choose your output. Right? So you can switch to vector graphics, or you can switch to a GPU like an OpenGL style output and WebGL. So that's a very nice organization. And just to mention that Makie is coming from, I think this is a name from a Japanese decoration technique. So you can, if you're interested, you can read about this in the Wikipedia. And so, for example, in Makie, it make one of the kind of useful feature that I find is that you can basically use any fonts available on your system. And this is quite different from other plotting packages that I have used in the past. In the past, when you use a plotting package, you can only pick, say, the available fonts in that plotting package. But in Makie's case, you can actually use all the fonts on your system. So for example, if you are on a Windows system and you have, the Windows system has a number of fonts, and then you can just name those fonts here. And then when you make a plot, you can just easily change the font, and then suddenly you have access to all of these fonts, right? So for some people, this is a way to make your font, your plot looks fancy. But otherwise, the basic functionality is similar to plots, but of course, by picking different backends, you do have access to some particular functionalities. To specify the details of a plot, the overall, the conceptual level is very similar to Julia plots, but then the detail, the syntax are different. For example, instead of calling the whole thing plots, the whole thing is called figure, right? And so instead of a size, this is called resolution. But you see the same kind of conceptual components are still applicable, but then the syntax are different. And so this is just a simple way to put your data and also run the regression. The last component of this talk, I want to mention something that is not exactly part of the Julia plotting, but I find this is a useful thing it's nice to be able to plot your data or make a plot after your computation directly coming from Julia. But other times, when you write your computation, suppose your code is written in Julia, and then the computation is quite extensive in a sense that the computation takes some time to run, and then after the computation, the data is output to a file. Sometimes the Julia's plotting capability is not sufficient for your need, and I will show you why that is the case. And so in those scenarios, you need another visualization software, something like a ParaView, something I happen to have example. So you need to have some third-party visualization tool that you need to use to look at your data. But you need to have a way to output your Julia data into a format that can be recognized by visualization software. One of the standard formats is called a WriteVTK format. And if you are interested, you can kind of look into the details of this. I just want to point it out. The whole documentation, and also there's an extensive wiki site you can kind of read about. So this WriteVTK format is one of the popular formats for visualization files. And in a few minutes, you will see the connection why I mentioned this, and make the connection to the Julia language. But for the WriteVTK files, WriteVTK is a number of file formats. So for image file, you have different formats of files for rectangular mesh, for unstructured mesh, and for like a parallel unstructured mesh. And so people use this for like a professional or visualization purposes. And this is useful because sometimes your visualization need is beyond just the XY plots. You need to have kind of do complex scientific visualizations. There are different software packages to do for scientific visualizations, but two of the popular ones, open source popular ones, and both are free. You can freely download to your computer. One is ParaView, one is Visit. And these two packages, both are based on the WriteVTK infrastructure, WriteVTK library. So if you write your data into the WriteVTK format, so one of those formats I just showed you, then the data can be easily loaded into PeerView or Visit software. And these two software, you can do very complex scientific visualization, right? Either for data analysis or just for visualization purpose. So you can make a movie out of your visualization. The VTK format is basically an XML style format. And so you can study that documentation, and you can write either Python or Julia, R, or Fortran C program to output your data in those formats, right? And since it's XML, if you just do this by hand, when I say by hand, you just use like a bunch of print statement, which is doable, but it's very tedious to write this, follow this format. And then I see a lot of kind of random character here because for data compression purposes, the data section is in binary. So that's why when you see this in a text editor, it's going to be all kind of random characters. These are quite tedious to create if you write your own code. But for Julia's case, there is a WriteVTK.jl package, which is quite mature and useful. The use case for here, I mean, at least for me, is that so you have your some Julia code, right? You have some data. Of course, the real code is going to be more complex. But suppose you have some XYZ data here. You can just put your XYZ arrays into this VTK grid, for example. This is one of the functions in the VTK, the WriteVTK Julia package. You can now output this file into a VTK format, and then you can load this format into your PeerView or Visit. And the usefulness of this is that the code is very simple, but then suddenly you enable the use of a powerful visualization software to inspect your Julia data. This is like just two simple examples, just show you how short the code is. So whatever you create, whatever data you create, you can just dump to the VTK function and then save to as a VTK file. So for example, I have a 2D array. So I have some computation, and this is this is closer to a realistic code. I have some function. So suppose I'm solving some equations or doing some computations, and then I can dump my data into a VTK file. Then I can load into my PeerView. And you can do the same thing for 3D, right? And if you have never done this before, you see that I have a 3D file, and I want to kind of look at my data, for example. And 3D data is kind of hard to look at, right? Because the data is inside, right? It's a 3D volume, and you can only see the outside. But you can actually, I happen to have done something here. So you can, for example, you can make the cuts, right? So you dump the data into a PeerView, and now suddenly you can use the PeerView functionality to inspect your data, right? So for example, you want to kind of quickly visualize your data. You can just operate this inside the PeerView. And my point is that from Julia code, 3D array in Julia code to PeerView analysis is only like 2 lines of code. Right? So you can very quickly access all the full functionality of another powerful visualization software, if the Julia plotting functionalities are not enough for you. This is coming to the end of my presentation. The entire Julia visualization ecosystem is quite promising. Like I mentioned earlier, Julia is a relatively young language compared to Python and R. The Julia 1.0 just came out in 2018, only 2 or 3 years ago. And also the same thing applies to its plotting or other ecosystems. But the entire ecosystem is quite promising in the sense that, so we had a new design of a new language. New design take advantage of all existing knowledge from other existing packages from Python and R. If you have used those packages in the past, and if you look at the Julia language, Julia package, you'll realize that it's pick and choose some good features from those kind of mature packages into the Julia package. And we briefly talk about several, only a number of plotting visualization packages, Plotly, Cairo, Makie, Plots, Plotly, and also some simple interface to VTK and pair view visualization. And also, we can make small, simple movies by few line of codes. Of course, more advanced one will be more complex. And two things that I didn't cover is the Vega Lite and Getfly packages. Both are very powerful, and the plots are also beautiful to look at. After this, I'm going to send you the slides and also the code example of Git repositories. So this will conclude my talk. I will be happy to take questions if there are any questions.